So good morning, I am Krishna. We continue to discuss cyclic decomposition of a linear transformation T belonging to M. Before we go into the cyclic decomposition, let us recall some of the basics that we have already explored in the last couple of lectures. When we recall the following, the D-cyclic subspace we defined a few definitions. D-cyclic subspace generated by a vector V is denoted by M V T, which is defined as the set of all GT V for G belonging to the polynomial algebra over F. Now, this is a subspace of which may not be equal to the whole of T. Now, if MVT equal to B, sorry, I think I got the wrong one. ZP. So cyclic space generated by V actually. Generated. If this ZVT equal to V, then V is called a cyclic vector. Now it simply says that using polynomials and the single vector V, one can generate the whole of, then we say V is a cyclic space. Okay. So remark, now there is another way in which Z can be, or the ZVT can be defined. So we observe it is the span of V that's it. Okay. Now one of the questions that immediately occurs is this. Does every T belonging to NT has this NT? If it has, then the problem is very simple. You can write the entire V as Z. But fortunately or unfortunately, it is not that simple. Even for, so the answer to this question is no. That is, if dimension of V is greater than 1, then the identity operator has because you see that we have seen that if the identity T is I, then V is any vector V, then you see that ZVT is essentially the span of V, TV is again V, T square V is again V. So it is just the span of the single vector V. But we have assumed that the dimension of V is greater than 1. Therefore, this doesn't cover the entire. Therefore, you see that with this the trivial example, it's here that given T belonging to LV, you cannot necessarily have a cyclic. There are some operators which do not have a cyclic. That makes the problem interesting. Okay. More generally, so we have discussed this earlier, so I am just recalling it. More generally, if T is diagonalized, I think we have discussed this. It's diagonalizable. Then T has a cyclic vector if and only if only if all the eigenvalues of T are so that doesn't happen. Then you see that you cannot have a cyclic. So this we have already explored and we have discussed in the last lecture. If further some more explanation about this, T is n eigenvalue which are distinct and the eigenvectors forms a basis for B, then equal to cyclic vector. That's a more detailed statement of what constitutes a cyclic vector in such a scenario. Now here what we have is PVI, VI, lambda 1, lambda 2, etc., lambda n are the eigenvalues. And you know that this forms a basis, and if you take the sum of the elements in the basis, that forms a cyclic vector. So we have got sufficiently deep information about this cyclic. Now we bring the polynomials into play, because you know that even in the definition of set P, the cyclic space, subspace, the polynomials are involved. Okay. So let us introduce the notion of what is called de-annihilator. Fine. So let M be a subcollection of polynomials G belonging to F of such that GT be equal to. So what you have is a single vector V not equal to 0. I mean, that's the non-trivial situation. And then you define MVT as the set of all polynomials in the polynomial space which annihilates V. Now this is what is called the annihilator formula. So what is involved is the following. So you have got V, the vector V, then you have got the class of all polynomials. You see T is given, so there is the collection called M. So this consists of all those G which maps V to 0. The zero vector. Okay. So this is again and this is a zero vector. So this is G which carries, this is GT. So GT is essentially equal to 0. Now it is easy to check that MVT is an ideal. Therefore, it has a generator, and the unique monic generator, monic polynomial, which generates MVT. Is called is also called the PNP, because you see that there is a unique polynomial that generates MVT, and therefore MVT can be easily identified with the particular unique monic polynomial which generates it. So both MVT and its generator are identified and designated with the same terminology called P annihilator of Bondy. Now there is no problem about it, because the choice of such a monic polynomial is unique, or there exists a unique monic polynomial which generates M. So there is nothing to that we have to do. Okay. Now what we look at is this. Now we have a nice bunch of results on this, some beautiful structures, and this is given in the following year. In fact, we have proved this here, so we'll just recall this. For V belonging to V not equal to 0, P belonging to LV, the P annihilator which is a monic polynomial which we designate by V of V has the property that degree of PV is equal to dimension of cyclic space generated by. Now this is a very important. It's connecting the dimension of ZPT to the degree of the polynomial that generates M, or what we call the cyclic, or what we call the PV. Now we have some more nice results on this. Further, if degree of K then we have our own specific information about the basis. Then what we have is that V so these k vectors form the basis for Z, that is the cyclic space generated by. That's very specific. K is the degree of the DNA of. It's a lot of connections between these things. But we explore. Further, we know that P of that means ZBT is invariant under P, and that's trivial rather, and if U is the operator induced by P, on ZBT, then of course what we can say is that the minimal polynomial for U is the same as PV. Okay. That's a very interesting. What we can assert is that the minimal polynomial for U is so this is a very interesting. Now we have already proved this here, so I must go through. So in fact we observe the following, some remarks we make some observations. PV is the P annihilator of it is also the minimal polynomial for U, where U is equal to P restricted to ZBT. And also, you know that the degree of PV equal to K implies the PV is also the characteristic polynomial. So this is the identification. It's a minimal polynomial. It is the characteristic polynomial of U. It is the minimal polynomial for U, or in other words, U has the characteristic polynomial and the minimal polynomial the same. Okay, right? That's also another interesting information. And now you know the structure of cyclic. It is spanned by the vectors V, PV, etc. e to the power k minus 1. And if that is the case, we can look at the matrix of summation for so our broad plan is the following. Our plan is D belonging to LB using operators having a cyclic vector. What I mean to say is the following. Focus. Let us assume T itself has a cyclic vector. Then what happens? You know a lot about it because it is spanned by, suppose V is that vector, then V is equal to capital V equal to ZVT, which is a cyclic space, and it is spanned by V, V1, V, PV, T square V, etc. T to the power n minus 1 V, that is, where n is the dimension of the vector space T. Okay? But suppose it is not the case. Then what one tries to do is the following. We try to find out, that is, we try to find out VR such that V can be written as that's the breakup that we hope to obtain. If so, you see that by what we have said, you have T reducing to U1, U2, etc., UR, and they are cyclic spaces associated with the operators U1, U2, etc., UR, and the vectors V1, V2, etc., generated by the vectors. So it is T, what you call UI cyclic. So ZVIT is essentially ZVI UI. Okay. But then you know about the basis for ZVIT. The basis for ZVIT is VI, EVI, e to the power ki minus 1 bi, where ki is the dimension of and ZBIT is the same as ZBIU. So this is the information that you have. So with this we can construct or we can get a basis for V. And now you see that if the representation of Ui, which is the restriction of T to ZBI, T, then you can use that to give a representation of T with respect to the basis B1, B2, etc. Br that we make using these sort of basis. Okay, and that takes it in a nice reduced form. Okay, so let us first explore how the matrix representation of U looks like. I mean, this is what we have again explored and studied in detail. So I just recall it because we need it. So there's some time gap now. So I just quickly recall this. And then we explore one example, take some insight into how we go about doing it. Now let us consider U. So we assume has a then you see that now here we are assuming dimension of V. Now this is a yes. In the beginning we have said dimension of V equal to A. For the analysis of this part, we assume dimension of V equal to A. Now you see that the minimal polynomial associated with T or U is then given by PV. Okay. So let us assume that PV is of the form C naught plus remember it's a model polynomial X. Now this is the minimal polynomial for U. Therefore, what we have is this. We have the following equations. Now we have the base is generated in the following form. So next we have the following, namely that is B1 equal to B2 equal to UB, B3 equal to U square, etc. and so on. And what we need is U k minus 1 equal to U to the power and you also have e to the power kV we also have e to the power kV minus Ck minus 1 e to the power k minus 1 minus therefore one can now represent U in terms of with respect to the basis where B is given by minus we have eventually 0, 1, then you have minus Ck minus. This is the structure of the matrix of this equation, and this matrix is called the companion matrix of so this is represented by the companion matrix of P. So eventually what we hope to have is the following. We can write, so eventually what we hope for as ZBR with the help of vectors belonging to them. Now we can take G reduced on each one of this to U1, U2, etc. UR. Okay. Then you see that each UI is represented by the companion matrix of certain the minimal polynomial associated with that cyclic space. So eventually what one gets is the following. So the matrix representation that emerges will be the following. So what emerges is the following. Then T, the representation for T with respect to the basis, which is the combined basis of ZB1T, ZB2T, etc. ZBR. So this is equal to into dot form events, right? Now what we have is this AI is the combining matrix of PBI, the minimal polynomial of P restricted to therefore you see that AI has degree, so AI is a Ni cross Ni, where Ni equal to degree of V. Okay, so this is what where AIs are the combined matrices of the polynomial. So we see that most part of the matrix representation has zeros, and each AI has a very nice structure, and we can make use of this representation. It's a considerable reduction from the general matrix representation that we may obtain on a daily basis. So here we would be, if we are able to get hold of V1, V2, etc. VR, which is our problem, then we will be getting a reduced representation. Wow. That's our concept. Okay. So the problem is now how to get hold of this. So we see that in the nutshell, the problem is this. We are going to have B written as the difference. You get, right? Where you have EW is contained in W, EW prime is also contained in W. So we represent the vector space V as the direct sum of invariant subspaces. Okay? So given one such invariant subspace, how to get hold of W prime? So that's the problem. So once we obtain W and invariant subspace V, how to obtain a complementary invariant subspace. We shall explore this point. So what we do is, before we go about exploring this problem, which is fairly involved, you will try to get some insight into it. So what we do is the following. Look at this. So the question that you ask is this. Our problem is reduced to when a D invariant subspace as a complementary subspace, which is also that's the question that we want to explore next. And so once we explore that, of course, how to do it. These are the questions that we want to. So before we explore this question, so what we are going to have is E written as W plus W prime. You know that we want W to be either a cyclic subspace or the direct sum of cyclic subspaces, which is invariant relativity. Then how to get another cyclic subspace, which which is complementary, or in general something complementary. Okay, so that's our objective. So we look at it. I'm not fully exploring this example, but only partially, and later we will consider this. So we take, let E be a linear operator on R3. Represent it. The matrix A Okay. 9 minus 6 minus 6 minus 1 4 2 explored earlier 3 minus 6 minus 4. With respect to the standard basis. Now we look at what is the characteristic polynomial as usual. This is how we try to understand a particular operator. And then once we get hold of that, the minimal polynomial, etc., and then try to get some cyclic vector if it exists. If it doesn't exist, you get a cyclic subspace. So this is what. Now we observe that this is all simple computation. Characteristic polynomial. Now the minimal polynomial now this is, of course, what you do is you verify this. That's a minimal polynomial, and you know that nothing less than that, no polynomial of degree less than 2 can be a minimal polynomial for this, because already you have x minus 1 and x minus 2 are factors in f, and therefore they should be appearing in B. So minimum there, the indices with which they appear should be equal to 1, and in fact we verify that it becomes a minimal polynomial. Okay, so having got that, what next? Now let us do some computations. First of all, we want to assert that this cannot be, R3 cannot be written as a cyclic space. It is not a cyclic space. That's clear from what we have done earlier. Now you see that this tells you that this is diagonalizable. Minimal polynomial is x minus 1 into x minus 2, and the indices 1 and distinct. It clearly tells you that T is diagonalizable. So let's try. But we see that it has multiple eigenvalues. Eigenvalues of multiplicity greater than 1. So 2 is an eigenvalue of multiplicity two, and 1 is an eigenvalue of multiplicity 1. What have we said earlier? In the last lecture we have explored this, found that if all the eigenvalues of T are distinct and T is diagonalizable, then V is a cyclic space, otherwise it is not. Okay? And we prove that R3 what we do is we start with a vector E1. So let us start with, so let me start with E1 equal to 1, 0. Good. See, we also observe that Z E1T has dimension 2 because the degree of the minimal polynomial that's a crucial. Now compute E1. What about E1? E1 equal to y minus 3. Well, that's easy to compute. And this is not a scalar modulo. E1. Therefore, they are linearly independent. Therefore, and the cyclic subspace or cyclic subspace generated by span of T1 for dimension 2 okay. And you see that this is equal to, so Z and 5 minus 1, this is E. And this is not equal to, so you see that this is an invariant subspace of, and that's the largest one that is generated like this. I mean, you can go only up to subspaces of degree 2 which are cyclic in this case because the minimal polynomial has degree 2. That's the reason. Okay. Now, how to find a complementary subspace? Which is Such a complementary subspace has dimension 1. Such a complementary subspace dimension 1. Why? Because dimension of Z E1 and the complementary subspace, because it's a subspace of R3, has dimension. Therefore, this is invariant under T. Therefore, this is generated by an eigenvector because it's of dimension 1, and you see that the T generates it. Therefore, you see that T E1 T, suppose if the vector is V, then TV has to be equal to a scalar times size. Therefore, what are the possibilities? There are two vectors that you can pick on. You have two eigenvalues here. One is E V or one of them will serve the purpose. Now you see that now 3 minus 1 3 is an eigenvector of T belonging to the eigenvalue but 3 minus 1 3 is an element of because you can write it as a linear combination of these two vectors. It's very easy. Very important. Therefore, it is not the eigenvector belonging to the eigenvalue 1 that generates it. So you don't get anything more. But still the gap is remaining. And therefore let us see what is the other possibility. 2 is the other eigenvalue. So let us compute the eigenvector corresponding. Now note that the vector belonging to the eigenvalue does not belong to which implies the cyclic space generated by 210 intersection cyclic space generated by 100, that is E1 T and in fact this is dimension 2, this is dimension 1, therefore they add up to make the R. And consequently it is equal to square now zero. The DE1 is 5 minus 1 3 and so that completes the effort of us to break up R3 as the direct sum of two cyclic subspaces. Okay, right. So this gives some indication, although it doesn't reveal too much, but we have not explored like this. Now we will explore how actually we tackle the main problem, namely given an invariant subspace, how to get a complementary invariant subspace. Now once that problem is solved, I think we have a way of getting hold of this V1, V2, etc. Vr such that the vector space V can be written as the direct sum of cyclic subspaces generated by V1, V2, etc. So, thank you very much.